Hi everybody, welcome to this course on modern optimization. The last lecture, if you remember, introduced what a genetic algorithm is. Today we shall discuss an end-to-end coding exercise whereby we shall show how to code up a genetic algorithm to do one of the most common tasks in data science, machine learning, and even statistics. And this task is called selecting features to build a mathematical predictive model that can be used to make predictions about a phenomenon of your choice. Not only that, but we shall also learn how to properly compare the performance of different methods for scientific reporting. We shall use three simple variations of genetic algorithm setups, and we shall see how to plot the graphs that properly show whether any of these variations performed better than others in a statistically significant way. So if you must write a report on the use of scientific methods, such as genetic algorithms, you will see how to report the results today. So let's get going, but first we briefly introduce what feature selection is, and the links to all the code that we are going to use are given in the description beneath this video. So like I said, we are going to practice applying genetic algorithms on the problem of feature selection. It is a very common task in data analytics or statistics. Suppose you have a bunch of measurements about human subjects. For example, these measurements are about age, weight, height, neck and chest measurements, and so on. Now the question is, the task facing you is that can you build a formula that takes these measurements and predicts the amount of body fat for a human subject? We can write like this, that we have to build a formula. In machine learning though, we do not use the word formula quite a lot. Instead, we say we have to build a model. Okay, so we have to build a model F that uses some or all of the supplied variables and predicts body fat. So our task is to find that F, but note, unlike in science where the formulas can be perfect, the models that we find in machine learning or statistics are not necessarily perfect. Okay, in fact, they very rarely are. And by that I mean, even if we get a great model, it will not predict the body fat perfectly, that is with zero error. However, because we have no other option but to use data science or statistical modeling to discover this formula, we will have to tolerate some error so long as this error is acceptable. So our task is to find the approximate model, not the perfect model, but an approximate model that produces the minimum error. In statistics, we often represent approximations with a hat on top of a symbol. So here f equals y hat. Y hat appears right at the end of the last item on the slide so far. So y hat represents an approximate model. This process of finding a model that predicts a real valued quantity, such as body fat in this example, by using data about a number of measurements or variables, this whole process is called regression. If you want to learn more about regression, I've put a link in the description beneath this video. So say we want to predict, want to find or guess the formula for computing a variable yy, which is highlighted on your screen inside a red rectangle. Here yy is the same as body fat, just the name has been changed. And we have to predict body fat by considering all the variables that appear to the left of yy. Okay, considering we'll later see we do not necessarily have to use all of them. Which of these variables can be used? That is that's what the problem of feature selection or subset selection is. So in any case, yy, and that appears on the right, is the output column, and all the other variables that appear on its left are the inputs. Now, regression will use this data to train itself and produce a good approximation, and will check whether that approximation is good, and that checking will happen inside the regression modeling, and that checking happens by comparing the output of the produced model that regression will produce, and it will compare the outputs with the actual outputs that appear in the YY column. So anyway, once we have the model, then we can use it to predict body fat for other humans for which we do not have all this data as appears in the table. Okay, but remember, regression is going to build a model, but I did say that we have to consider all these variables, and we are not sure which variable we should choose, or should we use all the variable. And regression cannot do that as selection on its own. Okay, that's where the GA will come in. Okay, right now I'm just explaining to you what regression does. So if we give all this data to regression, regression will use all the input variables and build a model using all the input variables, okay, to predict YY. So what can this formula or model be? Say we make a guess, at the start to begin. We haven't started doing regression yet, but say we make a guess. What could this model be? So we make a naive guess, and we just sum all the variables. Okay, so the measurements corresponding all these variables, we just sum them, and we say this sum will represent the body fat. Again, this sum is represented by y hat. That is y with a hat on top. Do you think it will be a great predictive formula? Will its predictions will be great? Well, it turns out it's not such a great formula, because the error between our guess y hat and the actual body fat, that is YY, is large. So what can we do? Well, we will use a technique called multiple linear regression. In here, instead of simply summing up all the variables as on the last slide, we multiply them with some numerical constants or coefficients, in the hope that if these constants are carefully chosen, the error in our predictions will decrease. So for example, in this formula on your screen, each of x1 to xk represent your variables from the last slide. So x1 is weight, x2 equals height, and so on and so forth. And the coefficients are represented by beta naught through all the way to beta k. They are, as I said, are coefficients or numeric constants that multiply with these variables. Now, if you find some really good values for these coefficients, then the error between our guessed formula and the actual values of YY, that is body fat, will be small. Now, to find these good values for these coefficients, beta, all these beta coefficients, we use a method called multiple linear regression. Okay, so again, multiple linear regression will only find the values of the coefficients. It is not going to pick and choose the variables. Okay, so if you supply it all the variables, it's going to use all the variables, and it's only going to come up with the best values of its coefficients. Okay, but a question is, do we really need to use all the variables to build this formula? Or can we ignore some variables and still build a great model, great formula? Okay, it turns out that often we do not need to use all the variables, but regression does not have the ability to select variables or select features on its own. Okay, but if we can use some technique to select a smaller subset of great features or great variables, then we can build a simpler model that uses less variable. Such a simpler model is easy to understand. As you can imagine, a small formula with a small number of variables, even from your science classes, you can remember that formula is easier to understand than a large formula with tens or hundreds of variables potentially in it. So the question is, how do we find which variables to use and which ones to ignore? Well, that brings us to the famous problem in machine learning and data mining, and it's called feature selection or variable selection. If you are being confused why I'm using words features, mixing it with variables, well, in machine learning, it is common to call a variable a feature. Okay, in statistics, we call it variable. In machine learning, we call it feature. Okay, but how do we select these features? Well, we can use a GA. Remember, a GA evolves solutions to a problem at hand. In this case, our solution can be a vector of ones and zeros, where a 1 means that the corresponding feature or the variable will be selected, and a 0 means that the corresponding feature will be omitted from our regression modeling. So if we consider this sample solution evolved by our GA, it means that our model will consider the variable x1 because there's a 1 in the first position. Also, it will consider variables x3, x5, and x7 because there are 1s in those positions. However, all the other variables will be ignored because there are zeros in those positions. If you are wondering about that coefficient beta naught, right after y hat, you might be wondering, well, there is no variable it is being multiplied with. Well, this is called the intercept term in linear regression. So if you remember from your high school classes on description of a line has a slope and a line has an intercept. So intercept is just a constant, it is not multiplied with any variable. Okay. If you do not understand that, do not worry about it. Just remember that an intercept term appears in the models produced by regression. Now thereafter, the fitness function of the GA will call multiple linear regression to build a model with the selected features. It may be a good model or it may be a bad model. But whatever the quality of that model may be, that quality will be reflected by the fitness of the solution. Okay, so for instance, this particular solution at the top of the slides, it will be sent to a fitness function, and the fitness function in turn will call a regression, and regression will build a model, and that model will have some accuracy or error, and that error or accuracy will become the fitness of this particular solution. The question is, how do you measure the quality of a model as proposed above? I was just saying that we can use accuracy or the error, but turns out there's more to it. We can get more sophisticated. Remember, our job is to actually minimize the features, to select as few features as possible and still be able to produce a great model. So how do we balance the accuracy as against a small number of features? Well, to do that, we can use a famous measure called AIC, or Akaike Information Criterion. You can find details about it on Wikipedia, but briefly, the AIC combines a model's error with the number of features that a model uses and returns a numeric value. So the lower this value, the better is the model on both these accounts. So that means a model that is accurate but also uses less number of features is better than a model that is accurate but uses more features. Hence, GA will use AIC as the fitness value and will seek to minimize AIC. Now let us see some code. So let's first consider the fitness function that we call feature fitness. Okay. It is defined at the end of the file called feature-selection.R. Like I said, the links to these coding files are in the description. So this function accepts 3 arguments. The first argument, named string, accepts a binary individual. Okay, that is a vector of 1s and 0s. The second argument, XX, is a matrix that contains the columns of all the features, so all the input variables that can potentially be considered for this problem. So all of them, they will come in. Okay, and YY, which just appeared right now on your screen, corresponds to the output or response variable. Okay, so linear regression will build a model to predict the values in this YY column. Next, we can scan the incoming individual or vector and note which features should be selected for building the model. Suppose the incoming solution has 3 1s at the first, the fourth, and the 6th positions. then the which command, which appears in the second line, the second blue line, will find these positions by checking which the indices of the positions that contain a 1. Okay, so the variable ink stores all those positions in a vector, and if you just print out ink, you can see that it has found out that the positions 1, 4, and 6 have a 1 associated with them. So only these features will be used by linear regression later. Now, if by chance we receive a vector with all zeros, then we cannot build a model because no features have been selected. In this case, we penalize such an individual by returning a really bad fitness value. Since the GA package that we use in this code only maximizes the fitness, that means it thinks a bigger fitness value is better, so we return a really small negative number. Okay, so a really terrible number. So to show that this is a really bad individual. Next, we extract the selected columns and ignore the rest of the columns when we use XX and the square bracket comma ink. Okay, so that is the effect of using that okay, as it appears on your screens. Also, we attach a column of all ones at the start with the help of the function cbind. This is required by linear regression function to compute the intercept term. Remember that beta naught that I was talking about? That didn't multiply with any variable? Okay, so to calculate that beta naught, we have to have a column of all ones. Linear regression will use that. Next, we build a linear model or the formula by calling the function lm.fit. Now, if you're wondering why we are not using the famous lm function that is commonly used to do the regression modeling, the reason is that lm function is relatively slower to execute. And here, because the GA will call this fitness function potentially thousands of times, going through all the members of the populations across several generations, so this fitness function is going to be called a lot. So we cannot have a slow function sitting in there because that will slow down the whole process. Instead, we use lm.fit, which is faster. Now, for this function, we also had to attach the column of ones, like I said. So, if you use the standard lm function, you do not attach column of ones to your data. But because of lm.fit, we had to attach it. Okay, so lm.fit returns the model with all the values of the coefficients that it has calculated by only considering the features that appear on your screen. Okay, so the GA individual selected the feature, and using those features, the regression method lm.fit produced a model. Okay, so that model is maybe good, maybe bad, we don't know. We also, there's a method called class. Okay, do not worry about it if you do not fully understand it. It just, defines the type of this model that has been produced. It puts a string ln just to show that it is a linear model. And finally, we call the AIC function to compute the AIC criteria. Now, because AIC has to be minimized, whereas the GA package that we are going to use actually maximizes the fitness. So to make sure that the two of them work together, we return the negative of AIC. Okay, so once we return the negative AIC, that means higher values are better. So the GA can continue as before to maximize the fitness of the individuals. Okay, so that completes the fitness. Next, we consider the code that sets the GA up before running it. This code is set up in the file called runGA.R, and it contains a function called runGA. But before doing that, make sure that the GA package is loaded. Otherwise, call the library function as on your screens. We assume that you've installed the package GA already. If not, do it by calling install.packages function. Now, the runGA function accepts two arguments. The first argument basically sets up the number of independent runs of GA that you want to conduct. The default value is 30 as it appears on your screen. Remember, a GA is a stochastic method. That means it uses random numbers to make various decisions. And therefore, running a GA, even with identical settings, can still produce different results. So to get a reliable measure of a GA's performance, we must run the GA at least 30 times with the same settings and report the average results. Therefore, the default number of runs equals 30, but you can change it when calling this function. For example, see a function call on your screens. And notice in this function call, we set the number of runs to 1. Notice also we did not change the original code, okay? And so shouldn't you. Just call the function in R console as on your screens. Likewise, furthermore, you can see that the definition of the runGA function has a second variable called problem, okay? And the default value of the problem variable is set up so that if you do not supply the value for this variable problem, it will consider that the feature selection problem with linear regression must be run. Okay, so this is the default value. Okay, but like with the number of runs variable, when calling the runGA, you can provide a different value for the problem variable as well. So you can run the same GA code for some other problems that have also been coded in this file. Next, the code checks if you have actually selected the problem to be feature, which is the default option unless you change it. Then the remaining code sets up the GA and defines different variables that will be passed on to the function GA later on. Okay, so small GA we are going to show you later on. That's a function call that will actually call the GA itself. So first off, we set maximum generations to 30. Note the use of double arrow there before 30 makes the variable max generations a global variable. So this, by global variable, I mean that this variable is visible outside the runGA function as well. And we do that because we are going to need the value of this variable later on for some other purposes. Then we set some common GA parameters. These parameters are population size, probability of crossover, and probability of mutation. You can change these options in the code if you want to. We set the type of the GA chromosomes to be binary because remember, we would want to evolve binary vectors. Then we call a function called getData. We won't go into the details of this function because it simply returns a matrix with a complete set of features as well as the output variable y. So, the data set that we saw a few slides back, that will be loaded and returned by this getData function. So this function getData is needed because every time the GA calls the fitness function, we have to supply the fitness function with a full feature set. So only a certain features from within that full feature set can be selected to build the model. Next, we separate out all the input feature columns. So this means all but the last column. Hence, we use -n call data. So if the number of columns is 14, then all but the 14th column are copied into the variable xx. That means, you just omit the output column and you just build a new matrix xxx that only contains the input columns. Okay. Likewise, we copy the last column separately into the variable yy. Okay. So, and finally, we tell the name of the fitness function that we are going to use. So as shown on the last slide, the name of the fitness function is feature fitness. Okay, so we supply that name here. Okay, so notice we are not calling the fitness function here. Okay, so there are no brackets in front of feature fitness, just the word feature fitness. Okay. Instead, we just write out the name here so that the GA knows which fitness function to call later on when it needs to. So next, inside the runGA function, we start a loop. This loop will run the GA multiple times. So if the number of runs equals 30, then this loop will run 30 times. When the loop starts, it prints out a message saying starting the run number and gives the number of the run. And then if we are running the feature selection problem, there's a call to the small GA function, the GA with written in small letters. And the results of this call are stored in a variable also called GA but in capital letters. Notice all the various settings that we did in the last slide. We are now passing them on to the function call to the GA. However, notice that while the genetic algorithm runs, it will produce different statistics like what is the best fitness, the average fitness, or the median fitness in each generation. So it will record those three statistics for all the generations inside a run. And so we need to record them as well. It turns out that the runGA.R records these three statistics in each generation in a matrix called this run results. And then when a GA run finishes, it dumps this matrix into an even larger matrix called results matrix, which is on the left. And it dumps it using the cbind function. So this way the results of all the different runs are added to the results matrix, and when the for loop terminates, the results of all the runs are available to you. These results are then plotted to collectively show the performance of all the 30 runs. Finally, we want to note what is the best solution produced by the GA or the genetic algorithm across all the different runs. Because we want to know what is the best ever that was produced, so we can use that. So we extract the best result produced at the end of all the generations in the present run by looking at the variable GA @fitness value. Notice capital GA is an object returned by the function call to the genetic algorithm earlier. The capital GA object in turn contains many variables, and the GA @fitness value shows the best fitness achieved in the most recent run. If this fitness is better than the best of all the previous runs, then we just update it. So let's run the code. To do that, source the code of both the files so R can run it. An easy way to do that is to press the source button for each of the two files. Remember, it is important that you source each file of the code that you want to run. Then let's call the runGA function. While for your investigations and reports, you must run at least 30 runs, here I just ran 5 to finish the runs quickly, and I'm using the feature selection problem. So as you press enter, here's a sample of output that will start printing out on your screens. Notice I'm only showing the output of 3 runs here because the remaining output does not fit the screen, but you will see more output on your R console. Notice each run is finishing after 5 generations because I set max generations to 5. Normally you will set max generations to say 20 or 30, or depending on what suits your problem. So like I said, that's because I set max generations to 5. And the reason I set max generations to 5 is because I wanted to show the results of multiple runs on the same screen here. If I had set a greater value for max generations, then many runs would not fit into this one screen. So this slide contains what's contained inside the results variable. Okay, remember when I called runGA, I dumped its results into this variable called results. Okay. So as we can see, the first column titled generation shows that each run goes up to 5 generations. Then the columns titled best one, mean one, and median one contain the corresponding statistics for run 1. Similarly, subsequent columns that come after these 3 columns contain these statistics for the other runs. The results for runs 4 and runs 5 continue below the other results. However, we report the results of a set of GA runs, and to do that, we often average the best results at each generations. So this means the average of the best results at generation 1 and the average of the best results of generation 2 and so on. So let me show you how to calculate these averages. But before doing that, let's note one last thing. Notice the best fitness first appears in which column? Well, it's column number 2. The column that is titled best 1. The column number for that column is 2 because the first column hosts the generations. So remember number 2. Secondly, how many runs did we do? Well, it is 5. So remember these two numbers, 2 and 5, for the next slide. So to compute the averages for the results that we have generated in the last slide, we shall use another function called parseData. This function expects 3 arguments. The first argument is data. Here we have to pass on our results matrix from the last slide. Next, we have to supply the index of the first column where the best fitness first appeared. And we recall that that index equals 2. Finally, we have to pass on the number of runs. And in this case, if you remember from the last slide, that is 5. However, remember for your reports, for your series reporting, the number of runs should be at least 30. Hence, we call parseData as on your screens and store the results in a variable P1 for later use. If we print out P1, it again produces a matrix like this. However, here the first column just repeats the generation numbers. The second contains the mean value. So in this case, it is the mean value of the best fitness at each generation. And finally, in the third column, we also show how much the best fitnesses were spread around the mean value. This is also called the error bar in statistics, and we shall plot these error bars later on when we graph the results. Now, before we start graphing, one last thing. Often in genetic algorithms experiments, we compare the results from different setups. For example, we may run one set of runs with a population size of 20. So we modify the code as on your screens. Now source the file after setting the variable pop size to 20. Make sure that you source the file. And then call the runGA function as is appearing at the bottom of the slide, and store the results in a variable called results1. Likewise, we repeat the process by setting pop size equals 50 and then 200. Like I said, remember to press source each time after modifying your code and before running the code in the console. If you forget to press source, the changes that you made to the code do not take effect. So finally, we have results from 3 setups. As before, we must parse these results before plotting. So we have parsed the data from 3 setups and stored them into 3 separate variables as on your screen. Now we are ready to plot, so we shall use another file called plotbars.R. This file has a function called plotbars, and this function expects that the parsed data output from the 3 variables on top of the slides will be supplied to it. Also, this function wants the labels for the 3 setups, so it can use those labels and put them in the graph that will appear later. So we call the plotbar function with the 3 variables and appropriate labels. Note, you must use sensible labels to make your graph readable. So we put the 3 labels enclosed in quotation marks because that's how we pass the text data in R. And there is our plot. Congratulations for getting this far. Well done. Clearly, we can see that the population size of 200 is doing the best because the average line is above the other average lines. But notice also that the error bars for the 200 population size does not overlap with the error bars below it. This means that the top graph is not just better, but actually statistically significantly better. Statistical significance is important to show when we show performance differences. Now, if you want to copy this plot from your R environments and you want to put that into your documents, just click export, which has a red triangle appearing on your screens. Just click export and it will give you different options to copy this plot. So if you want to know why does a lack of overlap of error bars shows statistical significance of difference, read up section 4.3 of the paper title that is appearing on your screens. Alternatively, you can consult a good book on statistics. I'll put a link to this paper in the description beneath the video as well. So that's it for this video. I hope you are ready to crack on with the code now. The links to the files is in the description of the video as I said before. So enjoy that and see you in the next video. Bye-bye.